Hello, my dear students, and welcome to today's coverage of our next topic in forces, which is now that we've made all of these compounds, both ionic and covalent, we now need to learn how to name them and how you can learn to do what I've been doing, which is naming all these compounds given their formula or deducing their formula giving their name. So what I'm going to do is go to your classroom stream and open up today's topic, and then when I'm done I will open up today's assignment and do it with you. So it will be fairly easy. So let me see. I'm using Google Classroom, and I am on my iPad, so we will see how things go as I progress through our topic. I'm going to do this as quickly as I can, and I'm going to try to use my Apple iPen, but it doesn't seem to be working well inside the Google framework. And right now, with this screencast, it's too much trouble for me to download everything and then reopen them up into appropriate programs. For example, this one into PowerPoint. So, I can't tell you enough how important it is to be correct in your terminology. You know me and you've listened to me and you know I make lots of mistakes, but I always try to correct myself to be as precise as we can, because in chemistry, simple mistakes can lead to, terrible consequences. So we have to have a universal language that gives us the common ground that we need to communicate scientifically. So let's get to naming ions. And then in the next one, we'll practice naming molecular compounds. Well, we'll practice naming ionic compounds, and then we'll practice naming molecular compounds. So the group A metals and nonmetal ions are, named, and what kind of ion they form depends on their position in the periodic table. The group A's are the simplest. We'll talk about some of the group B's transition elements in a minute. But monatomic ions have a single atom, a sodium atom, a potassium atom, an iron atom, an oxygen atom, a chlorine atom. And they lose or gain electrons to form ions. The number of protons never changes. If the number of protons changes, then we have a different element. So if you look at the group 1, they have 1 electron in their outermost shell. They're not going to pick up 7 to have 8. So what do? They lose that electron. If you lose something negative, you become more positive. It's the same with the group 2. They have 2 electrons. They're not going to pick up 6 to have 8 electrons in their outermost shell. However, I'm getting text as I do this, and there may be notices coming up, email notices and things, but we're just looking at my screen on my iPad here. So going back to our topic, the group 2 elements have 2 electrons. They're not going to pick up 6. That's too many to pick up to have 8 in their outermost shell. But if they lose 2 in their outermost shell, the next shell down has 8 electrons. And they have that noble gas configuration that is the most stable configuration. And likewise, the group 3, although there aren't a lot in group 3 to worry about, aluminum is one of the more common ones. They always form +3 ions because they have 3 electrons. They're not going to pick up 5. That's a lot to pick up. So they will lose 3. If you lose 3 negatives, you become a +3. You become a +3 ion. These cations, positively charged ions, for the groups 1, 2, and 3, you'll notice that their charge equals the group number. And all we do is add the word ion or cation to them. So we'll say a potassium ion, or an aluminum ion, or an aluminum cation, or a calcium ion. We just add the word ion to it to indicate they are positively charged cations. And because we know or can quickly use the periodic table to deduce what group they're in, we also know their charge because their charge equals the group number. So, for example, lithium, my Apple Pen is not working the way I expected it to, but lithium, sodium, potassium, rubidium, cesium, and francium all form +1 ions because they're in group 1. Beryllium, magnesium, calcium, strontium, barium, and radium form +2. And similarly, aluminum over there in group 3A forms a +3 ion. So if you have a group A nonmetal, they tend to form anions, and when they do so, there's several ways of looking at it. The official way to determine the charge on a nonmetal in the group A is to subtract 8 from their group number to get the charge on the ion. And then we don't say chlorine ion. It is a chlorine ion or a chlorine anion, but we change the ending to "ide." So we'll have chloride, fluoride, bromide, sulfide, phosphide, carbide, etc. when we form these negative ions. So, looking at this little bit of the periodic table, group 7 has 7 electrons. It wants to have 8. It picks up 1, so it'll have 8, but it picks up 1 negatively charged electron, so it has a net negative charge of 1. Now, that's the way I reason it out. Group 6 has 6 electrons. It wants to have 8, so it picks up 2 electrons to have 8, so it has a -2 charge. Or you can take that group number, 7 minus 8, for -1. The group 7s all are -1. The group 6s are all -2. 6 minus 8 is -2. The groups 5 are typically -3 charged. So nitrogen forms a nitride -3 ion, and phosphorus forms a phosphide -3 ion. So, excuse my touching the screen and changing the format, but these ions are all negatively charged anions because they are gaining electrons. And here's sort of an overview of what we've been talking about. +1, +2, +3 going left to right. And going right to left, starting with group 7, -1, then -2, then -3, all within those groups. Now, we're going to have to remember that when we start naming the compounds in our next topic. Now, the transition metals are a little more complex because they they can have multiple valences. They can be +1 or +2. They can be +2 or +3. They can be +2 or +4. And you can even have more than 2 valences for a few of them. So they're determined by what kind of compound they're reacting with and their origin, but we name them after the number of metals lost. Here are some typical beautiful transition metal solutions. These are obviously salts. They're not naming the counter ion or the anion. But going left to right, we have the color of cobalt, and then chromium, and then iron, and then nickel, and then manganese compounds. And you can see these transition metals, when combined with different salts, form beautiful multicolored, variety of colors, depending on the metal involved, that are great for pigments in paint. Some of them, in the older days, even toxic pigments in paint, heavy metal pigments, especially lead. Lead forms some brilliant colors. We'll see some of them in the lab, but unfortunately they were quite toxic, especially to humans, and especially to young humans. Lead is a terrible thing to have contaminating your environment if you are a developing human, because it causes terrible brain damage. So the question is, if you have more than two forms of a ion, of one of these metal ions in the transition metals, that's that big block in the middle of the group B elements, also known as the transition metals, how do you name them? Well, the classical method that I use, and I'm going to show you some examples here, involved naming them with the endings us and ik. So you would have cuprous, starting at the top right, cuprous and cupric. And you might say, okay, cuprous is always less than ik, so it must be one less. So cuprous is +1, cupric is +2. But then look at iron, ferrous and ferric. It's not +1 and +2, it's +2 and +3. It is true the ik ion, as in ferric or cupric, has a greater charge, but it's not, you can't assign it a specific value. The other thing is, if you look at plumbus and plumbic for lead down a little further, it doesn't, it's true plumbus has a lesser charge than the plumbic, but it doesn't increase by 1. This time it increases by 2. Plumbus is +2 and plumbic is 4+. So this classical naming system was unwieldy, required lots of memorization, and was very difficult to use and keep straight. I do have in the classroom an example of a toothpaste. I can't remember if it's Crest or Colgate. They use stannous fluoride, which is just a nice way of saying a tin 2 fluoride salt. Now the modern way is much better. It's called the stock system, and you use a Roman numeral to designate the charge. It's placed in parentheses after the name of the metal, between the name of the metal and the word ion, and the Roman numeral corresponds to the charge on that particular atom, on that particular transition metal. So I'm bouncing around here only because I want you to know about the stock system, and here's an example of it in the middle column. Copper 1. Hey, you tell me it's copper 1 chloride. I know there's a copper with a +1. Copper 2 chloride would have copper with a +2. And as soon as you tell me, what it is, lead 4 sulfate, I know that it's lead with a +4 charge and not lead 2 sulfate with a +2 charge. And I don't have to think back to the difference between plumbus and plumbic, or those charges are so different and start in different places and move different degrees, 1 or 2 charges difference, that it's hard to keep track of everything. So the new method is the only way we'll use it. It's the only way that's really used by the chemical companies or anybody who sells and deals with metals now, because it's one way to keep it straight, and if you keep it straight, you keep it safe. But that's the formal naming system, and we'll practice using it. This is a little question. Remember, I take my test questions from these lecture notes, and so it says, classify the ions as cations or anions and name the ion. Well, if you look at the periodic table, potassium is a group 1 metal. It forms a +1 ion, and it forms the potassium ion. Iodine is group 7. It gains an electron, so it forms an I, 1-, or just I-, the 1 is understood, ion, and that ion is named the iodide ion. Remember, we changed the end of the name to "ide" for the negative monoatomic single atom anions. For sulfur, it's group 6. It's going to pick up 2 electrons, so it's going to have a 2- or a -2 charge, and we're going to call that the sulfide ion. And lead can form several different ions, but in this case, it lost 4 electrons. That gives it a +4 charge, so that would be lead 4. It's pronounced the lead 4 ion, but it's written the lead, in parentheses, Roman numeral 4, close parentheses, ion. And we would not want to say plumbic ion anymore, because that doesn't give us the information we need. Okay, so here's another quick set of questions. Name the ions formed by these elements and classify them as anions or cations. Metals form positive cations. Non-metals form negative anions. So let's do it. Selenium is where is it in that periodic table? I want to say it's group 6, but I'm checking a periodic table right now. But selenium, Se, if you washed your head with your hair with Head and Shoulders or Selsun Blue, has selenium in it. And yes, it's group 6, so it forms a -2 ion called the selenide ion. Barium, of course, is group 2, and it forms a +2 metal. And phosphorus there is group 5, and it forms the -3 charged phosphide anion, termed simply phosphide. If you tell me phosphide, it immediately tells me it's made from phosphorus. It has a -3 charge, and it's an anion. Lots of information in a name. That's why the naming is so important. Now, here's a concept a lot of people find difficult, but many ions are not monatomic cations or anions, but polyatomic ions. It's a group of atoms covalently bonded together. We've already defined it previously in our studies. And the whole group of atoms stays together as a group, but it also carries a charge. Frequently, especially if these are, and most of them are, formed with oxygen, they have names that end in ate or ite. Not ide, ite. So ate or ite. So here's 4 polyatomic ions. The ammonium ion, NH4+. The nitrate ion, very common, NO3-. The sulfate ion, also one of the most common ones, SO4 2-. And the phosphate ion, which is PO4 3-. You know, sulfates are very common as fertilizers, but or components of fertilizers at least, and very common on sugars to make charged acidic sugars. Phosphate ions, phosphate is an important component of DNA. We have the sugar phosphate backbone in there. Nitrates play very important roles as fertilizers. Not as good as ammonium as a fertilizer, but it does have nitrogen for use by plants. But these are polyatomic ions. They exist together as a group. And if you have more than one of them in a chemical formula, which we'll get to, you'll put parentheses around it, as has already been done, and then put the number of them in a particular compound outside the parentheses, so you don't confuse the numbers, designating the number of each atom type within these polyatomic structures. So, the names, as I said, end in ite or ate, and here are many of the more common ones. You'll need to come back here to answer some of the questions to this table 9.3, but it has some of the more common ones. I want to point out one: acetate, sulfite, sulfate, nitrate, nitrite. Notice that when we have nitrate, NO3, the nitrite has one less oxygen, NO2. The sulfate is SO4. The sulfite has one less oxygen, SO3. Of course, 2- on the charge there. And nitrate has a single negative charge. But I would like you to go down and see the hydrogen carbonate. Many of these ions have trivial names, like the old classical naming system for the metal, transition metal ions. One name for hydrogen carbonate is bicarbonate. And the phosphates used to be called, they had different names, monophosphate, for example, and things like that. So The hydrogen carbonate's old name was bicarbonate. So if you add a sodium ion to it, you'd make sodium bicarbonate or baking soda. Its proper name would be sodium hydrogen carbonate, though. It's wonderful for relieving acid upset in someone's stomach. The bicarbonate anion is a big component of many antacids, particularly Alka-Seltzer. Some people just take the bicarbonate straight, put a teaspoon of water and drink it. Phosphate ions are important ions in your blood. We also talked about them being, and when they're hooked up and not free ions, a component of DNA. And, carbonate's an important one, too, in maintaining the pH of the blood, which is maintained over a very, very narrow range, and is extremely important. So we will talk about that in a different course called physiology. But those phosphate anions are called the monobasic and dibasic phosphate ions. That's the old name. Of course, they would now be called hydrogen phosphate and dihydrogen phosphate. They're an important component of fertilizers. If you have low phosphate or low sulfate soil, you'll add phosphate or sulfate ions. But, of course, the main component of fertilizers is something that contains nitrogen, because most soils, the nitrogen is limiting. Let me quickly answer these 3 questions. The way I've set this up, because I'm not actually presenting this the way I should, the answers will be shown, but maybe not now. When metals from groups 1, 2, and 3A form cations, the charge on the ion is equal to the group number. Don't forget that. And then, which of the following are positively charged polyatomic ions? Well, ammonium is positive charge, has a +1 charge, and has the formula NH4. Perchlorate is an anion, so it's negatively charged. You can look in that table to see that. And of course, the ferric ion, we would never use that term. We would say Fe Roman numeral 2. Roman numeral 3 for our ferric ion, but it is not a polyatomic ion. It's just a simple iron, so the answer would be 1 only here. Good test questions, as I'll remind you. If the name of the ion ends in ite or ate, the ion is a polyatomic anion containing oxygen. They left that part out, but that's an important part of it. So what I want to do is end this and go back to your classroom and discuss briefly your assignment that accompanies this. Now, my classwork and my appearance of my classroom stream might be slightly different than yours because, number 1, I'm a teacher. Number 2, I'm looking at it on my Apple iPad. So here is review of terms and concepts, and here is our form I'm going to open, and I don't seem to be able to write in it. I'm having trouble using my Google Pencil. Well, that didn't help me get to my Google Drive. I just want to see this. So what I'll do is I'll just talk you through it and share the answers with you so you can quickly get through it, and I will read this. So, ions that consist of a single atom are called, number 1, monoatomic ions. Metallic elements tend to lose electrons. Number 2 would be lose, L-O-S-E. Group 1A ions have a +1 charge, 3 is +1, whereas group 2A metals form ions with a +2 charge, 4 is +2. And group 3A metals, and we're really talking about aluminum there, form ions with a +3 charge. That's number 5 is +3. The charge of a group A nonmetal is determined by subtracting 8 from the group number. So 6 would be 8. And for example, the group 7 elements form ions with a charge of -1. So number 7 is -1 because 7 minus 8 is -1. Going on, many of the number 8 transition metals. So number 8 is transition metals. What are the elements with d electrons? Many of the transition metals have more than one common ionic charge. These ions are named using either the stock system or the classical naming system. And of course, you can reverse those. So number 9 is stock, number 10 is classical. But we're only going to use the stock system. Ions containing more than one atom, more than one atom are called polyatomic ions. So number 11 is polyatomic. And the names of most common polyatomic ions end in either ite, ite, or ate, ate. So 12 and 13 in either order. The answers are ite and ate. So I'll give you the rest of these answers, but if you will bear with me, you do have to listen to me kind of explain my reasoning. So the names of polyatomic endings end in ite or ate. That's sometimes true because I can think of like ammonium is ite, and some of them end in us, O-U-S, etc. So, and polyatomic ions for which there is an ite/ate pair, the ite ending will always indicate one less oxygen than the ate ending. That is always true, but you can't put an absolute number on it. Polyatomic ions are anions. That's sometimes true because there are some polyatomic cations. Ammonium is the classic example. The charge on the group A metals is determined by subtracting the group number from 8. That's never true. That would be the group A nonmetals. And the group 6A ions have a charge of 2 minus, and that's always true. So we have sometimes true, ST, 15 is AT, 16 is ST, 17 is NT, and 18 is AT. So moving on to our matching. Monoatomic ions would be B, ions formed from single atoms. That makes sense, pretty logical. Polyatomic ions would be E, ions formed from groups of atoms. Cations, number 21 would be D, positively charged ions. Number 22, anions would be negatively charged ions. That would be A. And number 23, a classical naming system, is C, a traditional way of naming transition metal ions, cations. And that's something we don't do. We use the stock modern official IUPAC system, International Union of Pure and Applied Chemistry. So, I'm sorry I cannot get my Apple Pencil to write on here. I'm not able to do it. I will get that working for the next one, but you'll just have to listen and follow along. What is the charge on a typical ion for the following groups? So group 1A always have a +1 charge. Group 6A always have a 2 minus charge. Going on to C, group 7A always have a -1 charge. And group 2A always have a 2 plus charge. And then it says write the name of each of the following polyatomic ions. So A is hydrogen carbonate. You can see that and how to spell it in the table. Its old name, like I said, is bicarbonate, but we don't use that anymore. So hydrogen carbonate. The next one is the ammonium ion. Not ammonia, but the ammonium ion, a positively charged polyatomic cations. The next one is called permanganate. It's got manganate is MnO3 minus, so this has an extra one, and we have some rules for naming them, but they get kind of complex, so we'll just leave it at, look it up in the table. It's permanganate, or Google it, if you're doing this online. And the OH minus is an ion you will come to know very well as we talk about acids and bases. It is called the hydroxide ion. So now the last one, number 26, is how many electrons does a neutral atom gain or lose to form each of the following atoms? So obviously calcium ion there with its 2 plus lost 2 electrons, because if you lose something negative, you get more positive. So A is lose 2. Sulfide has a 2 minus, so it must have gained 2 electrons, so it's gained 2. The iodide ion there, so don't forget sulfide and iodide, we changed the name, the ending to ide. So C, the iodide ion, it gained 1 electron. It got more negative, but you're gaining a negative. So when you add a negative, you get more negative. So gained 1. Just think the same way you do in math about gaining electrons. Don't forget they have a negative charge. So manganese is plus 3, and it lost 3. So it will lose 3 electrons. The answer to D is lose 3 for that Mn. By the way, that's manganese, not magnesium. Magnesium is Mg. So when you're looking on the periodic table for these, for information, Mn, make sure you match up those symbols. That's a common beginner mistake, manganese versus magnesium. So, this concludes this screencast. I will stop us here and try to get back to our classroom, and I will be posting the 2 video discussions for the lab, and I still have to make one for the most recent lab, and I will be posting them as quickly as I can, since each of these takes several hours to upload. Until the next video, stay safe.